evening, everyone. Today we will talk about how to solve circuits in the S domain using Laplace domain techniques and Laplace transform techniques. And yeah, it's very similar to what we did with differential equations. Differential equations are just an intermediary step in solving a circuit. So if you have any general circuit, right, and you're finding some output, let's say VO of t, and in this case we're solving the transient in general, so we're going to go back to the time domain, and you might have some input Vn of t. The idea is that we can take all those inputs or and outputs, all those signals. For circuits, the signals are really voltages and currents. We can take all those signals and transform them to the Laplace domain, right? And then solve the circuit in the Laplace domain, and then go back into the time domain, right? There's just special things we have to be aware of, special treatment we have to be aware of, and how to handle the initial conditions of capacitors and inductors. So if we know how to handle the initial conditions of capacitors and inductors in the S domain, we are set to solving any problem, any transient problem using Laplace domain techniques. That's the only kind of like special thing that we need to understand to be able to effectively solve circuits in the S domain. Of course, other than that, we know, I mean, we could always derive the Laplace domain equivalent equations just from the time domain equations, right? So any voltage signal, Vt, Vit, Vot, I1t, I2t, we can transform to the S domain. So and the convention is to use capital letters in the S domain. So we have Vis, Vos, I1s, I2s, right? And then there's also the basic circuit elements. So we have the resistor, right? So the resistor is has Vt and then It. So for the resistor, Vt equals Rit. In the Laplace domain, the resistor will look like this. Vs equals Ris. Nothing fancy here, nothing changes much. Where things change are for inductors and capacitors. So for an inductor, we know that VL equals L dIL over dt. Those are functions of t. In the Laplace domain, this will be VL of S equals L, and differentiation is just multiplication by S. So it's going to be LS, or let me say SL ILS, right? So the concept of impedance arises naturally in the S domain. SL is what is called the impedance, right? Right, and remember that we for AC analysis we designated S. We said S equals J omega, right? So it turns out, remember when we found the integral formula of the Laplace transform, we have a parameter S for the Laplace transform. It's mathematically S is complex, could be complex. So S exists rather than existing on a real line, exists on a complex plane. Right? So this is what's called the S plane. Right? So AC analysis really what AC analysis boils down to is analyzing circuits only on the imaginary line where S equals J omega. Right? For us to do transient analysis, proper transient analysis, as we did in the last lecture, we have to consider S to live on the whole plane rather than S being just on the j omega axis. Right? Constraining S to be in the j omega axis is what gives us AC analysis, essentially. Okay. So that's a bit theoretical, but it's something that you should keep in mind. And that's why j omega, remember when we introduced S, we introduced it as a shortcut for j omega. That's not the full picture. The full picture is that S really represents the Laplace transform forms of the signals that are functions on S, where S is a variable, unlike T, S is a variable that exists over the whole complex plane. Okay. What about the capacitor? The capacitor has IC equals C dVc by dt, therefore ICS equals SC, differentiation becomes multiplication by S, VCS. Again, notice it's much simpler. It becomes multiplication, it becomes algebra. And this shows up as the impedance in the S domain of a capacitor. And all the rules about summing impedances and paralleling impedances and all of that follow in the same way. Okay, all the circuit rules follow. Now this treatment is not yet complete because we have to take into account the initial conditions. Right? We want to solve transients for circuits in general, but we cannot do that unless we take into account initial conditions for the inductor and the capacitor. For the inductor, the initial condition would be IL at 0, and for the capacitor, the initial condition will be its voltage at 0. Right? We somehow have to incorporate those initial conditions into those elements, and then we can use the S-domain techniques to solve transients in general. And there's a bit of subtlety here that we have to explain. So let's talk about what we want to talk about is models of L and C in the S domain with initial conditions. We have to treat initial conditions if we want to solve transients for transients in general. Okay, let's start. So we want to start with modeling inductors and figuring out how to inject the initial conditions, the initial condition of the inductor in the model, in the S-domain model of the inductor, right? And the way we approach that is by noting that in general, this would be the VI equation representing the inductor. And then this would be what it looks like as an integral, right? So the initial condition appears here. And the idea is that we want to, in the S domain, we want to figure out a way to inject in the S domain model. We want to figure out a way of injecting this initial condition. There are two approaches. We can either inject the initial conditions based on U of t, based on the step function, or we can inject the initial condition based on the delta function, and I'll show you how to do both. Right. So if we consider that the current passing through if we consider this component, the integral, to be the current passing through the symbol, the inductor symbol in the circuit. So if we consider in the S-domain model, if we consider this integral to be represented by the current passing through the inductor symbol, right, then we can represent the initial condition as an extra current that's being summed to this current. How do we represent an extra current summed to another current? Well, when two currents are in parallel, they sum up, right? So this is how we sum the initial condition to the current going through the inductor symbol, which is just the integral. Okay, so this is what the model is going to look like, right? And this is in the time domain. So I have the inductor symbol representing the current passing through it. This arrow here is just the integral of VL, the voltage across the inductor, right? The symbol by itself only represents the integral, right? Only represent the current that goes through the symbol only represents the integral. I have to account for the initial condition. I account for the initial condition by adding a current source in parallel. So the total current of the inductor is going to be the initial condition current plus the inductor current. So this is a valid way of modeling the initial condition. And when I go to, this is the T domain, when I go to the S domain, I just, IL0 is constant, U of t, that translates to IL0 over S. And then the impedance becomes LS, right? And the current going through the inductor symbol is just VLS over LS, or VLS over SL, right? LS is or SL is the impedance of the inductor, right? So this is the S domain model that's based on the unit step function. Okay. We can do a similar treatment for the capacitor. So this is what the integral equation for the capacitor is going to be. The voltage across the capacitor is going to be this integral plus this initial condition voltage. And we want to follow the approach where the symbol, the capacitor symbol in the S-domain model is going to only represent the voltage that is due to this integral. So I want to model my capacitor as a symbol of a capacitor with something else, and this capacitor symbol, the voltage across the capacitor symbol, only represents the integral of the current flowing through the capacitor. How do I account for the extra initial condition? The extra initial condition is just extra voltage that's summed up. When do voltages sum up? Voltages sum up when they are in series. So the initial condition will be in series with the capacitor symbol, right? So in this case, the total capacitor voltage is going to be the voltage across the symbol plus the voltage source that represents or models the initial condition, right? So this whole thing is going to be the total capacitor voltage. However, the voltage across the capacitor symbol is going to only be the voltage due to the integration, right? So that's the trick, right? And then we translate this easily to the, of course, this is U of t because it only appears, we're only interested with things happening after everything starts. We're solving circuits assuming that everything is zero, and then once it hits zero, we plug in all the initial conditions. The initial condition itself can be anything. VC0 can be anything, but in this model, because we're multiplying it by U of t, nothing happens for t less than 0. It's easy to go to the S domain now. It's just going to be integration turns into multiplication by 1 over S. So we have 1 CS, ICS over SC. This is just a matter of turning integration into 1 over S. We've established that. And then the impedance is 1 over SC, of course. That's we derive that easily. And then the initial condition is modeled by this voltage source, which is VC0 over S. Right? So this is one way of modeling the initial conditions using the step function. And the models are for an inductor and a capacitor are going to look like this. There is another way to model the initial conditions, which utilizes this delta function. This works in the following manner. The ID, first let's revisit what we established. The symbols themselves in the circuit, in the S domain, just represent integration or differentiation. So for an inductor, the current passing through this inductor symbol is just the integral of VL, of the voltage across the symbol. The voltage across the symbol, notice. And then the current passing through the voltage across a capacitor symbol in the S domain is just the integral of the current passing through the symbol. Now, the idea is that we need to feed the initial conditions to those symbols. And the initial the initial condition for an inductor is what? Is a current. So we want to feed this into the symbol, which is an integration. What's the best way to feed something through an integral? Is to feed it through the delta function, right? If I have the delta function inside an integral, I get a constant, either 1 or whatever. If I have some function here, I get f0, right? So the idea here is for an inductor, for example, to imagine the circuit with the inductor to look something like this. So I have the inductor, I have this here cloud that represents the whole circuit. This cloud appears as a voltage across the inductor. This cloud or black box that has all the complicated circuit in it just appears as a voltage V circuit across the inductor. Okay, so this is the rest of the circuit. Now I want to add a voltage source in series. It has to be a voltage source because the integral for the inductor has a voltage in it, right? So I need to add a voltage source in series with the inductor with an impulse in it, with a Dirac delta function in it, such that initially at time equals 0, I have the voltage due to the circuit, but I have added to that voltage due to the circuit an impulse. And the only purpose of that impulse is to inject the initial condition into the inductor, right? So this impulse goes into this thing, 1 over L VL dt 0 to t, right? So this VL V circuit feeds into it, that's fine. But other than V circuit, we also have this feeding into it. What is this voltage, extra impulse that's feeding into it? Well, this is L I0, right, delta t. L cancels with L. That's the reason I put L here, to cancel with the 1 over L. And then I0 delta t, I can take I0 out. Integral of delta t is 1. Right? So I end up with IoT. Right? So the current through the inductor symbol will have an initial injection into it of the initial condition due to this impulse voltage source. Same thing with the capacitor. The capacitor might be connected to some circuit. This blob represents the circuit. This whole circuit has an equivalent current that it presents to the capacitor, right? So this is what I call the current from the rest of the circuit. In addition to this current, I want to add an impulse current in parallel with the circuit current, just to inject the initial condition, nothing more. I only want to inject the initial condition. So this symbol is just 1 over c integral of the current passing through the symbol. The current coming from the circuit does its thing. We don't care about that. But the current coming from this extra impulse shows in here. So this is C VCO delta t. C cancels with t with c. That's why I added the extra c. And then I end up with the VCO outside, and then integral of delta t is just 1. So this is how I get the initial condition injected into the capacitor model in the S-domain. In summary, the S-domain models are going to look like this. So for each element, there are 2 different models depending on how I want to inject my initial condition. If I want to inject my initial condition using a step function, I'll do this. I'll use those 2 models. So it's either going to be a inductor with a parallel current source or a capacitor with a parallel voltage source. And notice this is ut. That's why we have the 1 over s. Or we can use this. This is based on ut. Or we can inject the initial condition based on delta t. Right. So in this case, we will have the inductor symbol in series with a voltage source, impulse voltage source. Here I'm writing everything in the S domain, not in the time domain. Or a capacitor model in parallel with a current source. So in the time domain, this would be inductor, and then the voltage source will be LIL0 delta t. Right? Any constant in this domain is going to be some delta t. right? Because 1 goes to delta t in the time domain. So this is the summary. Those 4 models are the summary of how you would model those elements, basic elements in the S domain, inclusive of the initial conditions. Okay, let's do an example to make this clear. So the example is as follows. We have the circuit, and we want to find the complete transient response in the, using the S-domain technique. So we have an input that's a cosine omega t, u of t. Previously, when we analyzed such a circuit, we were only concerned with the steady-state AC response, right? But now we want to analyze it in a more complete manner. We want to find both the steady-state response and the full transient response. And the Laplace domain technique, the Laplace transform technique, allows us to achieve just that. Right, so in this case, omega is just 2 pi 60. This is a 60 hertz electrical system, right, which equals 377. We have a resistor, 1 ohms, an inductor, 1 millihenries, and a capacitor, 100 microfarad. So we want to find VO, the output across the capacitor, VOT. Right, and I'm going to give you initial conditions. IL0 equals 1 amp and VC0 equals 2 volts. This is the voltage across the, and this is IL. So the VC is the voltage across the capacitor. Right. So all we have to do now is redraw the circuit in the S domain. So that was what we drew in the time domain. The S domain, the model is going to be, circuit model is going to look like this. So the input VIS is just going to be, and it's just a matter of taking the Laplace transform of the cosine. So this is going to be S over S squared plus omega squared, where omega is 377, right? And then the resistor is just a resistor. Now, because this is a single loop circuit, we have 2 options for modeling the inductor. We can either take this model or take this model, right? I prefer to take the second model, the impulsive model. Why? Because that will maintain everything as a single loop. It will not, this thing, if I do like a parallel current source, that will complicate the circuit a bit more. It will introduce extra meshes. This will keep the circuit, the second option is going to keep the circuit as a single mesh, single loop. So I'm going to use the second option for modeling the inductor. So I'm going to have the inductor, which has an impedance of Ls. So this is going to be 10 minus 3, which is 1 millihenry S. And then I'm going to have the voltage source for modeling the initial condition, which is going to be L, IL0. IL0 is 1 amp. L is just 10 to the power minus 3, 1 millihenry. Okay. And then I'm going to model the cap. And here I'm just going to use the first model because it maintains the single loop. The second model in this case complicates the circuit a bit more, introduces an extra mesh. So I'm going to have the capacitor with an impedance of 1 over SC, which is 1 over 100 microfarads, 100 times 10 to the power minus 6 S. Right, and then the initial condition is just the voltage in series, which is 2 over S, right? So it's VCO over 0 over S. So the initial condition of the voltage is 2, so it's going to be 2 over S. And that's it. Of course, V out T in the S domain is going to be, oh, by the way, this in the S domain is the model for the whole capacitor. Right, so V0 in the S domain is going to be across both the capacitor model in the S domain and the extra voltage that represents the initial condition. So this is going to be VOS in the S domain. Right? Remember, because those 2 elements are put in instead of the capacitor, right? Okay, so and we're ready now to solve the circuit. we can solve it in an intermediate manner. So we can first solve the loop current IS, and then multiply this IS by the impedance of the capacitor, and add to it the voltage representing the initial condition. So what would IS be? IS would be just simply VIS divided by the total impedance, right? Well, it's not just VIS, it's going to be the total voltage, right? So it's going to be, so I have VIS. Let me write what VIS is. VIS is just S over S squared plus omega squared. And then I have the other voltage that I need to sum, which is plus 10 to the power minus 3. And then I have a voltage that I have to subtract because it has an opposite direction, right? So this is going to be let me see, minus 2 over S, right? And then divide that by the total impedance, which is 1 plus 10 to the power minus 3 S plus 1 over 100 times 10 to the power minus 6 is going to be 10 to the power 2 minus 6, 10 to the power minus 4 S. Yeah. All right. So this is going to be 10 to the power minus 4 S. Let's see. We can simplify this a little bit. So what I can do, what can I do? I can multiply everything by S, right? So I end up with S squared over S squared plus 377 squared. I plugged in the value for omega, plus 10 to the power minus 3S minus 2 divided by S plus 10 to the minus 3 S squared plus 10 to the power 4. So I took the 10 to the power minus 4 to the numerator, right? And then I want to kind of like, I need to get it ultimately in the form of a polynomial over a polynomial, but I'm not done yet. I'm trying to solve for VO, right? So I'm trying to solve for VOS. So I just need to take this and multiply it by the impedance, right? So what would VOS be? VOS would just be IS times the impedance, which is 1 over 100 times 10 to the power minus 6s. We said this is equivalent to 10 minus 4, right? Plus 2 over s, right? This is what VO is going to be. Right, so this is what VOS is. It's IS times this impedance plus this voltage representing the initial condition. We said this is what the whole VOS is. And it's going to look something like this. Right, so we can simply plug this IS here to get the value for VOS. So we need to do a bit of polynomial manipulation here, but that's fine. We can do that. So this is going to be s squared over s squared plus 377 squared plus 10 to the minus 3s minus 2 over s. Let me rearrange this. Start with the highest order. 10 to the minus 3 s squared plus s plus 10 to the power 4, right, times 1 over 10 to the minus 4 s plus 2 over s. Okay, so how do we approach this? Well, we need to do another simplification. I need to multiply everything by s squared plus 377 squared. So I end up with s squared. I need to multiply the numerator and the denominator by s squared plus 377 squared. So I end up with s squared plus 10 to the minus 3s, s squared plus 377 squared minus 2 s squared plus 377 squared. Right, so I multiplied both the numerator and the denominator, so I'm going to have s squared plus 377 squared times the other polynomial, s squared plus s plus 10 to the power 4, right? And then this whole thing is multiplied by 10 to the minus 4 s plus 2 over s. So notice it's kind of a little bit hairy, but we can do it. That's fine. So it's going to be VOS equals. Let's see what we can do with the numerator. What we can do is we can expand everything and then collect the polynomial. So what we can do is we can have s squared plus 10 to the minus 3 s cubed. So this turns into a cubic equation plus 377 squared times 10 to the power minus 3 s, right? So 10 to the power minus 3 s cubed, and then 10 to the power minus 377 squared s, and then minus 2 s squared minus 377 squared times 2 plus 2 over s, right? Divided over, let's try to simplify a bit. Let me take the 10 minus 4 in. So I end up with s. So I have s and then s squared plus 377 squared. And then I have, right, I have s squared plus 377 squared, and then I took the 10 to the power minus 4 in, so it becomes 10 to the power minus 4 minus 3 minus 7 s squared plus 10 to the minus 4 s. 10 to the power 4 times 10 to the minus 4 is just 1 plus 1. Okay, and we don't have to. We're gonna do partial fraction expansion anyway, so we don't have to get this into a final polynomial. We can leave it that way, and I guess we can collect the numerator. So VOS equals, I can collect all the powers of s. So I have minus 2 s squared plus s squared, so this is going to become minus s squared. So it's this term and this term. And then I have one s3 term, so it's going to be 10 to the power minus 3 s to the power 3 minus s squared. Okay, and then there's an s term, which is plus 377 squared 10 to the minus 3 s. It's this term. And then there's a constant term, which is minus 377 squared times 2 plus 2 over s. So this is the numerator polynomial, and then in the denominator we have s squared 377 squared 10 to the minus 7 s squared plus to the minus 4 s plus 1. Okay, this would be VOS in the time domain, in the S domain, and finding all that remains now is finding VOT in the time domain by taking the inverse Laplace transform of this expression, right? I'm not saying it's an easy thing to do. It's a bit of a hairy expression, but we could always go back to MATLAB or Mathematica and try to use that to help us factor out those expressions. So the goal here now to kind of go back to the time domain is to come here, and 2 over s is easy. 2 over s is just 2u of t, right? So here I'm gonna want to try to kind of do a partial fraction expansion. What do I need to do? I need to kind of express VOS as expanded into fractions of s. So this is going to be a over s plus, and then s squared plus 377 squared. This is going to be bs plus c, right? And then I'm going to have a third expression, which is this 10 to the minus 7 s squared plus 10 to the minus 4 s plus 1, right? And this is going to be ds plus e plus 2 over s. And if the goal now is to find the constants a, b, c, d, e, and if I find those constants, I can work on getting the inverse Laplace transform. So let's do that next. Okay, I want to utilize MATLAB to aid me with this symbolic calculation, with this algebraic manipulation. And I'm going to show you how to do that. A nifty thing in MATLAB or in Mathematica, if you want, you can do symbolic manipulations. So the first thing you need to do is you need to define a symbolic variable s. So this s is just a symbolic variable. Let's call it s. Right, it's symbol s. And that's so you store in s, in the variable s, the symbolic value s, and this allows you to manipulate a bunch of symbolic expressions with s. So the goal is, we said we wanted to kind of like get the numerator. So we did the partial fraction expansion, and then we combined it together to get the numerator in terms of constants a, b, c, d, and e, and then we want to solve for those constants. So so yeah, what would the numerator be? The numerator would be a times the other two denominators, which is s squared plus 377 squared, right? And then times the other denominator, which is 10. I guess we can say 1e minus 7. That's how you write 10 to the power minus 7 in MATLAB, times s squared plus 1e minus 4. That's 10 to the power minus 4 times s plus 1. Aha, so I'm missing something here. I need to define the variables a, b, c, and a, b, c, d, e to do a full symbolic manipulation. So I'm going to define a as being sim a, b as being sim b, c as being sim c, d as being sim d, and then finally e is just sim e. Okay, so I have all the symbolic variables defined, and then I can go back. When I do this expression, I can see that it does it for me. Now, that's not the only thing I want. I want to also to be able to expand this expression into a polynomial. So the function to do that is expand. So when you do that, it should expand everything into powers of s, as you see here. It kind of gives you like numbers that are fractions because it's trying to do a symbolic calculation. I know in Mathematica sometimes you can convert symbolic calculation into numerical calculations. I'm not sure if you can do that into numerical decimal point numbers rather than doing rational fractions. But let's stick with this for now. Okay, we're not done yet, right? We want to get we want to get the full polynomial, right? So this is going to be plus, right? This is a, but then we have the other, we want to get the full numerator, right? So we have still bs plus c, and this thing is multiplied by s and multiplied by this polynomial. Right? I'm just combining all the partial fractions together to get one polynomial in the numerator that I can compare with the original numerator to get the constants, the values for the constants a, b, c, d, and e. Right? So this is bs plus c times s, and then times, I said, this expression. Right? And then finally, I'm going to have d times s plus e times s times the other expression, which is this one. Let's see. Yeah. So this evaluates fine, but I want to expand it. So I want to go and apply, feed it to the expand function, and I get this expanded expression. So this is, yeah. Oh, yeah. Let me see. Is there? I think there's a collect function and so collect answer s. I'm just checking if there's a collect function. Oh yeah, there is a collect function in I'm familiar with the collect function in Mathematica. The reason I'm using MATLAB at this point is because well, I mean, you have more access to MATLAB anyway, but my license expired for Mathematica. I typically prefer Mathematica over those things. But yeah, there is a collect function. It allows you to collect everything as coefficients of s. So this is what the numerator polynomial would look like. Okay. Okay. So we said this is what the numerator is going to look like. I was interested in seeing if we can represent it in using decimal numbers. It turns out we can. There's a function called VPA that allows us to do that. So if I say solution equals let's call it numerator, num equals collect. I guess I have to go back up here. So expand. Right, so the numerator is just this expression we said, and then we can take this and collect S, right? But furthermore, we can convert this into, this is correct, but we prefer to convert this into decimal numbers instead of symbolic fractions. So I think 1 designates how many significant digits. Oh, this has to be 2 at least. Right? What happens if I put 5, let's say? Yeah, I think this is just a matter of the significant digits. So you have 5 significant digits. I think 3 is good. 3 significant digits is good. Right? And this is the full numerator. And now we are ready to kind of like write a bunch of equations to solve for those constants. Okay, so I'll copy this and we'll start working with it. Okay, so I've copied the result we got from MATLAB into OneNote, and yeah, all we have to do is this would be the numerator after we combine those three expressions together, and it's just we have to compare it now with this polynomial. So off the bat, that we see that 1.42 times 10 to the power 5a equals what? Equals 377 squared times 2. So that tells me that a equals 377 squared times 2 over 1.42 times 10 to the power 5. Right? So this is the value of a. We can calculate it later, but let me write down all the equations now. So we found a, right? And then we can, start one by one. So see the terms of S. S has A, C, and E, right? So S has 1.4, sorry, has 14. This is the terms of S. This is 14.2 A, right? We already know A, plus C plus 1.42 times 10 to the power 5 E equals what? Equals 377 squared times 10 to the power minus 3. We're comparing with this numerator, right? And this gives us an equation of C and E. So we have C plus 1.42 times 10 to the power 5 E equals 377 squared 10 to the power minus 3 minus 14.2 A. We already know what A is. So this is just an equation that has C and E as unknowns, right? Now we take the factors of S squared, and this is A is known, B, C, and D are unknown, right? So actually, I think it's probably better to write everything as actually, I think, yeah, there's a better way of solving this. What we need to do is we need to write everything as a matrix equation, right? So what we need to do is we're solving for those constants A, B, C, D, E. So we need to fill in components of a matrix here, and then put in the numerator coefficients here. So here we're gonna have 10 to the minus 3, right? The coefficient of S3, and then minus 1, and then this is the component of S. Let's see. Yeah. So we have, how many equations do we have, by the way? So we have 5 equations for each coefficient, and we have 5 unknowns. So it makes sense, right? So so we have all the way up to S4, right? So the coefficients here of we have the coefficient of S3, the coefficient of S2. Oh, so let's start with 0, right? Because the coefficient of S4 is 0, and then the coefficient of S3 is 10 to the minus 3, and then we have minus 1 coefficient of S squared, and then we have the coefficient of S, which is 377 squared, 10 to the power minus 3, and then the constant, which is minus 377 squared times 2, right? And we fill in the numbers from this, and it's just a matter of inverting this matrix to find all the constants A, B, C, D, and E. So I can show you, I can go back to MATLAB and show you how to fill in those matrices. So let's do that now. Okay, so we're back to MATLAB, and we said, hey, we wanna write everything using a matrix equation so that we can solve the constants. So first we wanna fill in the matrix M. Let's call the matrix M. So I'm gonna fill it in. So I have to fill it in with the coefficients of A, B, C, D, and E, right? And for every coefficient for every coefficient of S. So the first row now is going to be represent the coefficient of S to the power 4. So that's going to be, well, I'm going A, B, C, D, and E, right? So I'm going to start with 1 E minus 7. That's the first, that's what's A multiplied with. And then I'm going to have another 1 E minus 7. And then I'm going to have, there is no C. So you can see here that there is no C here. So I'm going to have 0. And then D is 1. And then E is 0. That's the first row. Second row here, all I'm doing here is I'm filling up the matrix, right? That I'm going to invert to find the constants A, B, C, D, and E, right? Then I'm going to, in the second row, I'm going to look at the coefficients at the expression that is the coefficient of S to the power 3, right? So that's going to be 1E minus 4, and then again another 1E minus 4. And then C is going to have 1E minus 7, and then D is going to be 0, and then E is going to be 1. And then the third column, the third row is going to be S squared, coefficient of S squared. So it's going to be 1.01, 1 E minus 4, and then D is going to be 1.42 E5, and then E is going to be 0, and then that's S squared, and then S is going to be 14.24a. There is no B. C is 1, and then there is no D, so it's going to be 0, and then E is going to be 1.42 E5, and then finally the final row is going to be, there's just A there, so this is going to be 1.42 E5, and then B is 0, C is 0, D is 0, E is 0. If everything is correct, we should get 3, 4, 5, 5 by 5 matrix. Let's check if we do that. We do that. We do get that. Okay, and then we want to find we want to compare that to the numerator. So the numerator, let's call it num. So that's going to be the row vector. That's going to be well, there is no S4 in the numerator, so it's going to be 0, start with 0, and then the second row is going to be the S cubed coefficient, which is going to be 1e minus 3, 10 to the power minus 3, and then the second row, which is the S squared coefficient, is going to be minus 1, and then after that it's going to be the S coefficient, which is going to be 377 squared, I believe, times 1e minus 3, 10 to the power minus 3, and then the final one is going to be 377 squared times 2. 377 squared minus 377 squared times 2. So this is the numerator. And then the solution for the constants a, b, c, d, and e is just going to be inverse m, and this is matrix multiplication times num. So when we do that, we get the value for all the constants. So now we're done. We notice that a, b, c, d turned out to be 0, which simplifies things a bit. So I can copy this, and now I go back to OneNote again. So just to link to what we did in MATLAB, this was the matrix M, what we populated in MATLAB, and this was the num vector, right? And we just inverted M to get A, B, C, D, E. So this is A, this is B, this is C, this is D, and this is E. So I can now finally write VOS as well, A is just minus 2, so it's going to be minus 2, well, minus 2.0018 over S, and then B is going to be plus B is what is so I have BC, so B is going to be 1.0062 S plus 14.63 over what, S squared plus 377 squared, and then the third one is going to be, we said D is 0, so we just have a constant 0.0011 over 10 to the minus 7 S squared plus 10 to the minus 4s plus 1 plus 2 over s. Okay, and now we can, we're done. Now it's just a matter, so this is going to be, when we do the inverse Laplace transform, this is going to be a u of t times some constant. This is going to be a combination of sine and cosine. We did that last lecture when we solved the differential equations. This is going to be also a combination of sine and cosine or exponential, depending on the roots. So depending on what the roots of this polynomial are they complex conjugate, or are they roots that we can find, right? And this is going to be u of t. Okay, so we know now how to do this. Let's kind of simplify a little bit more. So VOS, so minus 2 plus 2, I'm going to end with what? With minus 0.0018 over S. plus 1.0062s plus 14.63 over s squared plus 377 squared plus 0.0011 over 10 to the power minus 7 s squared plus 10 to the minus 4 s plus 1, and that's it. Okay, I can simplify this a little bit further. I can multiply this by 10 to the power 7, so I end up with so this is going to be yeah, so this is what, this is 1.1 times 10 to the power minus 3, right? That's what 0.001 is. It's 1.1 times 10 to the power minus 3, because we go back 3 times, right? 1, 2, 3. Right? So minus 3 plus 7, 10 to the power 4, so it's equivalent to 1.1 times 10 to the power 4. Then I multiply the denominator by 10 to the power 7, so this is going to be 1. So it's going to be s squared 10 to the power 7 times 10 to the power minus 4 is going to be 10 to the power 3 plus 10 to the power 7, right? And yeah, just cleaned it up a little bit. Yeah, and just like as I said, it's just a matter now of finding the roots of those polynomials, right? Or really what we can do is complete the square here. It's in a similar manner to what we did last time, and that will allow us to kind of find the form of this and do the inverse Laplace transform. Okay, this we already know is a combination of sine and cosine, because now I can do this. I can take VOS, so I know this is 0.0018 over s. This is a u of t. I can separate this, so I end up with 1.0062 s over s squared plus 377 squared. I instantly know what this is, right? This is cosine 377 t u of t, right? We established that. Of course, times 1.0662, and then plus 14.63 over s squared plus 377 squared, okay, plus 1.1 times 10 to the power 4 over s squared plus 10 to the power 3s plus 10 to the power 7. Okay, so we know how to do the Laplace transform of all of those expressions. So this is going to be minus inverse Laplace transform. This is going to be minus 0.0018 u of t. This is going to be 1.0062, and this is s over s squared plus omega squared. So this is going to be cosine 377 t u of t. This now is going to be 14.63 divided by 377, because I can divide by 377. I can do this 377 over 377 and take the 14.63 divided by 377 out, and I end up with omega over s squared plus omega squared. So this, I end up with 14.63 over 377 times sine 377 t u of t. So this is simple. The last one is a little bit more complicated. We just have to kind of do what we did last time, which is I won't repeat it. It's exactly the same thing we did last time when we solved differential equations. We have to do we have to complete the square, and then write this in a way that looks like some constant, some constant. Let's say f over s plus something squared plus something, or minus something. If it turns out to be minus, it's going to be real roots. If it turns out to be positive, it's going to be like a bunch of cosines and sines that are shifted in s, meaning they'll have some e in them. Okay, so I'm not gonna repeat that because this is a repetition of what I did the last lecture. I'm already over time, but yeah, I can leave that as an exercise. This part I can leave as an exercise for you. Okay. So with that, we're done with this discussion and introduction to using Laplace domain techniques for solving circuits. It's pretty mechanical, as you can see, and hopefully straightforward. It is cumbersome, I will admit. So in the exam, I wanted to give you like a complicated example, just to give you like a very general case. But in the exam, I would give you like simpler circuits with simpler inputs that will be at most second order. I will try not to give you something that will go to third or fourth order. So yeah, but I wanted to give you like a bit a bit of a complicated example to show you the technique. All right, with that, we're gonna have our final on Thursday, next Thursday, and with that we're gonna end this summer course. And yeah, thank you for paying attention, and good luck on the final. Thank you, guys.